Okay, everybody, thanks for coming today to our virtual simulation lab seminar. Today we have Chris Daub from the Department of Chemistry. He's going to be talking to us about curve fitting with xmgrace. Most of us have to do curve fitting at some point in our careers. So this should be a broad bit of interest for most of you. So at this point, I should stop talking and give it over to Chris. Thank you, Chris.
Thanks for coming. I work over in the chemistry department with the ATK group, and came over from Canada, did my PhD at UBC. I guess I first got interested in doing more interested in curve fitting than most people when I was taking, I did a course in regression analysis when I was an undergrad, and found it much more interesting and useful than any pure math courses I was taking. So I like to think that since then I've developed a bit of a knack for how to do curve fitting, especially with the kind of calculations that you do as a modeler, whether it's in physics or chemistry. I think it's a slightly different problem than people doing experimental work where you have a bunch of scattered data and you're just trying to find some kind of trend line to put into it. When we do calculations in our field, we tend to get much more smooth data, and there's no statistical error to speak of, but so there's obviously some kind of function that should describe this set of points, but you don't know what that function is. So the questions you need to think about when you're doing this is, what makes one functional form better than another? Which one gives me more information versus which one gives me a perfect description of the data without really helping me understand the problem? So that's the kind of things I'll be talking about today. And the tool I'm going to be using to talk about curve fitting is called xmgrace. It's not just for curve fitting, it's for doing all kinds of graphs. And I like it for doing, when I'm trying to make a graph look nice for publications, it's my tool of choice. It won't do three-dimensional plotting or anything like that. If you need to do that, you've got to pull out the big guns of Mathematica or whatever. But for 95% of my problems, xmgrace works pretty well. If I just need to do a quick and dirty plot of my data as it's coming out of a simulation, for example, then I'll use NuPlot or something like that. But it's really hard to make something look good with NuPlot. So here's the home page for Grace. The history of this program, it started out as a program called xmgr, and then some people made it a little bit more user-friendly and changed the name. It's not under a lot of heavy development anymore. I think the last stable version came out in about 2008. There have been a few bug fix versions come out since then, but there's still a fairly active forum community. There it is, forums. So, there's people talking about stuff on there. There's a user community, and they've written some scripts to do for, sometimes there are things that the base version of Grace won't do very easily. But you can go on the forums and find somebody who has dealt with your problem before and can show you how to do it. So it's a Linux program. So if you're using a Mac or any form of Unix with Ubuntu, you can use apt-get to install Grace. With Red Hat, there's an RPM that people have written for it. So to run it, I would just go into my terminal here and type xmgrace. And it opens up a window. Up here there are some tool tips. So a file would be, to open a new, the files in xmgrace are called, they have the extension AGR. So I could go here and open up a .agr file, save things. For printing, it's nice because I can export the graph in a variety of different formats. So if you wanted to glue this into a latex file, you can just directly print out an EPS here, change all the resolution settings and stuff like that. So yeah, basically I'm just going to show you live how you would analyze some data. And here's an example of some data that I have. So I go to import, ASCII data, and what I'm going to load up here is I do molecular dynamics simulations. So one thing I'm doing right now with some simulations is computing the dipole moment of my system, the total dipole moment, and computing a time correlation function of this thing. So it looks like this. So it's normalized to start at 1 and then decay down towards 0 as time goes on and the dipole moment of the system changes away from what it was at time 0. There's a bunch of different columns in this data set. So I go down here to block data, and it's going to auto-scale it automatically when it reads it in. Sometimes you want to do that, sometimes you don't. And I want column 6, that's where my data is sitting. Apply, and I get...
So you get that window because it's block data, right?
Yeah. If I just did a single set, then it would automatically assume that I want column 1 and column 2, and just load that up.
Is there any delimiters that are necessary in the file?
I don't think so. I think it's just if there's a space between the number, it assumes that. It's not particularly robust. If you have any ends in there, it's going to complain and stuff like that. So sometimes you have to edit your data beforehand. Yeah. So here's the data. So I've got my correlation function over here, and this is, in this case, it's time. So maybe I want to put some labels on those axes. So I go down here to axis properties, my x-axis. I'll label that with a T in, I think this is in femtoseconds. Actually, let's do it this way. So I can show you how to do a superscript. There's a sort of a cryptic way of doing various formatting of the numbers, changing fonts, putting in Greek symbols, all that stuff, mostly involving backslash. So I do FS, backslash, capital S to do a superscript, -1, and then I backslash N to stop doing a superscript. And then my closing parentheses. Did that work? Yes, it did. Good. And then I can do something similar on the y-axis. So this is just going to be, let's call it C of t for a correlation function. There. I can make that larger over here. Axis label, character size larger. And it gets larger. So when you do a correlation function, usually looks something like this, something relatively like an exponential decay. So I can see that more clearly if I change the y-axis to logarithmic. And I don't need to show, I can change the start and stop of the axis to a little bit of a different value. I can change the spacing here, so I have a bit more of a reasonable, there. So this is what I'm left with.
Can you put that in the markers too? So
What's that?
can you put that in markers so we can like see the points individually?
I think there's a hell of a lot of points here, but I can do that. Set appearance, symbol properties, let's make them circles. Yeah, but there's like 50,000 points here, so it just looks kind of bad. All right. So if this was a simple, what's called a Daub relaxation, it would be a single exponential thing, and this would be a perfect straight line. But as you can see, it's not a perfect straight line. But I can still try to fit it. So now we'll get to the curve fitting part of things. I go up here to nonlinear curve fitting. So the way this works in xmgrace, so I pick the set. This is the data set that I've loaded up. So this is my source set, and the destination is where the function that I fit is going to end up popping up. I want to fit this as an exponential form. I've written it here. So that's 2 parameters. And it's just going to assign names for these, arbitrary names for these parameters. So I have an A0 and an A1 now. And now I write the formula I want to fit. And so one thing that makes this kind of nonlinear curve fitting different from what you do if you're doing the kind of like a linear regression or a fit to a polynomial is that those kinds of fitting problems have exact solutions. You have, if you're doing a straight line fit through some data, you have, you compute the difference of the difference of squares between your points and the function you're fitting. And if it's a linear regression or a polynomial or a few other forms, there's, you do matrix algebra to compute the exact set of coefficients in the polynomial that will best fit that data. With nonlinear curve fitting, there's no exact solution. So what it's going to do is sort of an iterative approach, and it's going to sort of do a parameter search in order to find the best fit to the data. And so it's not a black box. It's much more, it's something you have to sort of look at the resulting fit you get and decide, well, that looks right, or that looks not right.
Initial guesses, I assume.
Yeah. So sometimes you have to, it'll work better if you put in an initial guess here. So actually this A0 is one is actually a pretty good guess for what this initial number should be. Like A0 times the exponential of so A0 times 0 should, well, e to the 0 would be 1. So if A0 is 1, that's a pretty good first guess. I'm not exactly sure what A1 should be, so I'll just leave that at 1 and see what happens for now. And if the first guess was not very good, I can't even see where the function it tried to fit is. But now, as I repeat, see, it's only doing 5 iterations at once, but it's gradually getting closer. You can see the line it's trying to fit is just barely showing up over here. And now, it finally managed to get something that fits a little bit better. I repeat that a few times. You can see these numbers still slowly changing. I can crank up the number of iterations. It doesn't really take that long for this to go. And it's really not changing anymore. So it really does look like this is the best I can do with a single exponential. So with problems like this, with a time correlation function, what people often say to explain why they're not single exponentials is that there are multiple different relaxation processes happening here. So the longest time scale relaxation is something like a Daub relaxation in a liquid. And then there are shorter time scale things happening. So this is often, so people say, well, maybe it should be multiple exponential terms. So instead of a single exponential, I might want to add an extra one. So let's see what that does. I'll increase the number of parameters to 4 now. And write in another exponential here. And let's see how that does. There we go. So clearly it's a much better fit. It's getting so by combining two different exponentials, it's doing much better. My decay constants here, they're different by about a factor of 5. So there's a shorter component here and a longer component here. Another thing people sometimes do with this kind of problem is, instead of a sum of exponentials, there's something called a stretched exponential form. So that would be only 3 parameters. So I still have a single exponential, but what I do is I come in here and I put a power here, A2. I think this will work. So yeah, so the fit looks just as good, and one measure of that fit would be this correlation coefficient. It's not particularly informative, but if you're trying to decide between 2 different functional forms, if one of them gives you a better correlation coefficient, then that's some reason to believe in it a little bit more. And another thing I like about the stretched exponential in this case is that it's giving me a very similar quality of fit with less parameters. Maybe you've heard this expression before. I just looked it up. With 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. I always thought it was Enrico Fermi, and he is the one that said it, but he attributed it to John von Neumann. So it's not actually an original Fermi-ism. But I think there's a lot of truth to that. With enough parameters, you can fit anything. So if you're making a choice between a function with 5 parameters and a function with 3 parameters that work equally well, you might want to go with the one with less parameters, just as a rule of thumb. I mean, it's Occam's razor, essentially. The least complicated solution that fits the data is probably the one that you should work with. Okay. So I think that's all I wanted to show with this data set. Now I'll show you something different. A different problem that I was working on. Did I want this one? I think I want the other one. Here we go. So, I got this data from a grad student in our group. He's doing he's doing quantum chemistry calculations of the interaction between a platinum atom and a graphite surface. So he takes this platinum atom and moves it at different distances from the surface, and he computes the potential energy of that interaction, and he gets a curve that looks like this. So that's just a bunch of points. It's very useful to be able to fit that to some kind of functional form. What should that functional form be, and how do we find it? So I could just go in here to my data again, transformations. Let's try just regular linear regression. And if I insist on making this a linear fit, well, I get some kind of point, some kind of line. This is exactly the same as what you get with Excel, for example. If you just try to do a fitting in Excel, you'd get this straight line.
This is the exact solution.
Yeah, yeah. But there's only two parameters, and it's clearly not a linear function, so you're only going to do so well. I can do a little bit better if I fit it as a quadratic. I mean, if I assume this was a harmonic oscillator, I would want to try to fit it as a quadratic. It gave me an error because I didn't select the set I want to fit, so I have to actually go here and click on it. So now I get this. I tried to set those defaults differently, but it didn't work. What I just did was go into the plot directory. This is where you change a lot of the appearance of the plot. So I can change the whole plot. I can change the particular graph I'm looking at. I can change the axes. I showed you a little bit of that just now. Or I can change what the set itself looks like. And so I've gone in here, and I just want to change the color of that to something that actually shows up well on a presentation like this. Let's just make it black, and we can change the line style here. We can make it thicker. There, that looks better. So that's my exact solution for how to fit a quadratic equation with 3 parameters to this data. It still doesn't look very good. So one thing to think about when you're doing curve fitting is, what part of the data am I actually concerned about? Do I really want to fit this whole thing, or do I really want to concentrate on understanding what's happening near the bottom of this potential well? I mean, that's where this platinum atom really wants to sit, and that's the potential it's going to vibrate within, for example. So maybe I don't care what happens up here, and maybe I don't care what happens up here near the inner wall, and I should just focus on what's happening here. I can do that within xmgrace by defining regions. So I go here, regions, define. I can define this region in various ways. I'm going to define it as a horizontal range. So I click here, define again. Now down here it's saying pick the first point. So I'll pick one, like, let's say there. And then I go over here, I pick the second point, let's say right there. And now, so this arrow tells me the region I've defined. So now I can go up here, and in restrictions, I can say just fit region 0 that I defined, and still do a quadratic fit. And now I just did that fit, and I'm getting this blue line. So I'm doing fairly well now, but it's still not an exact fit. But it's much closer than this one was, because I've decided to focus on a smaller region of my data. but you can only do so well with a harmonic. This is a harmonic potential assumption, basically. So it's going to, what we're assuming there is that the potential is symmetric. Clearly, this isn't the case. If the platinum atom goes far enough away from the surface, it's just going to go off into infinity, as shown by the potential way up here. So what I really want to do is fit this to a anharmonic oscillator model, and one example of this that is very popular is the Morse potential. So that's this function here. If I did a Taylor expansion of that, the first term of it would be the harmonic oscillator approximation. So that's one justification for why this potential form is nice and useful. So let's go back to the nonlinear curve fitting. I'll take the initial data and choose that as my source set. The destination, actually let's overwrite one of these data sets because I don't really care about this one anymore. So that was the set that was the quadratic curve I did second. I'll just click on that, and now I'm going to overwrite this set with whatever comes out of the fitting here. And there's going to be 3 parameters in this function. 3.
You always have to call your parameters A0, A1, A2.
I think that's the default here. I'm not aware of any way to change it. But it's just, I mean, it's arbitrary. So, yeah, in the actual Morse potential functional form, this is the dissociation energy. So it's the difference between the zero of energy, which I've defined to be at infinity, and the bottom here. The A2 parameter is the equilibrium distance from the surface to it's the location of the minimum of the potential, and A1 is the spring constant for the potential. It tells you how wide this function is. The -1 sometimes doesn't show up in the definition of the Morse potential. In this case, I'm using it in order to make the zero of energy, the arbitrary zero of energy, be at infinity. So that's why that's there. Let's see what happens if I do this. So its first attempt, not so great. Let's see what happens if I just repeat it a few times. It's getting better, getting better.
Is this giving the region that you defined favoritism?
No,
okay.
no. This is again fitting over the entire region, but it's not too terrible actually. There are more complicated extensions of the Morse potential that are sometimes used to describe the entire region of a potential like this, but then you're introducing more parameters. So again, it's a trade-off between whether do you really need to describe the data accurately using 50 gazillion parameters, or are you better off having a simpler form that actually gives you some information that is useful for some other theoretical purpose you might have. Yeah, and again, I can focus on this smaller region. So that would be, there's an advanced tab here. I click on that, and I say I want to look at only region 0. And Yeah, you can do some pretty funky things. You can weight the different points with different values. You know, if you, for example, you might have some data that's more reliable than other data. You could change the weighting. But I think that's all we want to do for now. Let's overwrite this red line. So I'll click on the red line I made before, apply, and so the new fit I've gotten is, well, you don't have to take my word for it. Let's change the, what I can do is go up here to plot, axis properties, and I'll just change the range I'm looking at. So I can home in on the first angstrom and a half of data I have, and I can change the y-axis as well. Let's just go up to 100, let's say. You always have to click apply every time. It's easy to forget to do that, and then you have to go back and do it again. So now you can see that when I focus down on this region, my red line is a much better description of the data than this dashed black line that I made before, which was trying to fit the entire curve. So if all I'm concerned about is getting a very good description of this relevant region, this red curve is doing a pretty good job now. And I can, where was it? Transformations. When I go back to this dialog, and it's always another useful thing to do is just check these numbers and decide in your head whether they're reasonable or not. So this A0 ought to be the bottom of the well, and it's giving me 157, and negative 150 looks like a pretty good guess here. The A2 should be the distance of the minimum in the x-axis, 0.76, and this is 0.5, so that looks pretty good too. The A1 is a bit more difficult to think about just in these kinds of qualitative terms. But the A0 and the A2 at least make intuitive sense just looking at the data. Okay, I think that's all I wanted to show with that. Let me show you one other example for fun. So this is just to show you in a bit more detail the kind of things you can do to make a publication-ready graph. Yeah, I don't think I'll go into the. This was research I did for a paper a few years ago. We were looking at it was a nanoparticle suspended in water, and we apply an electric field, and because there is a difference between the dielectric properties of the nanoparticle and the solvent, the nanoparticle wants to orient itself parallel to the electric field. And these, this is the probability distribution of that angle between the particle and the field, and you can fit that to a Boltzmann equation and find out that it should be a Gaussian distribution around 0. And so the data that I got out of my histogram of those angles is the dots, and the lines going through it are the functional fits that I get to this function. So clearly it's a pretty good approximation. And you can change this A1 parameter into a torque, and I can actually compute the torque directly from my molecular dynamics simulation, and they agreed quite well. So that was nice to be able to put into the paper that you had two different routes at getting the same number, and they agreed quite closely. But that's neither here nor there. What I want to focus on is just showing you how you can make nice plots that will be publication quality. So you can change the size of the plot. If I go into graph appearance, I can change in this viewport here. I can change, so if I make this 0.3 instead of 0.4, it's going to make the graph a little bit wider. Changing these tick values to be pi by 4 and pi by 2 is a little tricky, but you can do it. I go into plot, axis properties, x-axis, and over here in special, I can change, I can make these whatever I want them to be. So instead of 45 degrees, I want it to be pi divided by 4. To make it a symbol font instead of the regular font, I do \x, and then p will transform into pi, and then I do my \n to go back to regular font, and then divide by 4. And I did the similar thing here at 90 degrees, change it into pi over 2. And I did a similar thing here to change the, to make the x-axis to be an angle phi, \x, f, and something similar in the y-axis here, p, \x, that's an f, and then \n to go back to regular font. Changing the line, like the thickness of the frame around this plot can be done. I go to plot, graph appearance, frame, and then changing the width here. So then it gets thicker. Sometimes you want it to look like that. So there are different frame types I can use. So you can see that this is a fairly flexible tool for doing all kinds of different things. Let's say I wanted to just put in some new, write something in the graph to point out some interesting data. So I could go up here to text, and now it gives me a little prompt here. It says pick beginning of text. Let's start it there. And now I've got a chance to put in some text. And once I've done that, and so I can change things here. I can change the size. I can rotate it if I really want to. And then if I want to do some sort of finer tuning of the location, I can actually go in here and change by hand the numbers. So if I want to shift it over a little bit, I can do that. Yeah. I can change, I've got a legend box here. I can go in here and I can change the location of that. The actual legend titles get defined in a different way. Close that box. Plot. So in the set appearance, when I define this stuff, that's when I put in the string that I want to put on the legend. Should I keep going, showing stuff, or
No,
I mean, how long is this supposed to be good?
It's
Yeah.
getting cold, so.
Okay.
Yeah. So, okay, guys. Thanks for coming. I hope we got a good introduction to xmgrace today. Like I said earlier, curve fitting is something that we all do. Does anyone have any questions for Chris? Yes.
In which format can you export that to PDF or can you?
Yeah, there's a bunch of different ways. I go over to File, Print Setup, PostScript, EPS, PDF, JPEG, PNG, many different options. So for plugging into LaTeX, I usually just export as an EPS. Journals always complain about the resolution not being high enough, so I just make it 600 DPI. You can choose to export as landscape or portrait. Yeah, you can change the file name of the file you're printing out here. Yeah. But it's a two-step process. There's a print setup, so I do that, I apply that, close, and then to actually print it, I go back up to File and Print. And then over in my, if I quit xmgrace, I won't quit it yet, just in case there's some other questions, but the file will show up in the same directory that you're working in.
Yeah. If you export to APS, why do you still need to specify DPI? Because it's vector-oriented, right? So you can zoom in infinitely.
Yeah, but
Or is it the fake APS?
I'm not sure. I know that that changes the file print setup. I mean, this is just how I do it, and it works. If I change this here, if I make this back to 300, then it's going to change the dimensions in pixels. So I go here, I say I want to print out letter format. It changed these numbers. So it's actually printing out less pixels when I change the DPI. So I guess maybe it's not DPI. It's like it's relative to the size of the paper I'm printing out. But I know I've had problems when I don't make this. When I don't change the resolution and then I try to glue this into a paper and I can see the pixels. So I just do this and I don't see the pixels anymore. Yeah.
Is there any way for me to use these, especially the nonlinear curve fitting? Can I call any the root functions in xmgrace from, say, a Fortran or MATLAB program?
I don't think so.
And,
I mean, maybe, but
and
I've
just
never tried.
Put in the vectors as my data set and have it fit. Because myself, I don't have such a nice equation for a nonlinear model. I have to do those all out by computation. So every time I want to do a fit, I have to generate a curve from a quick continuum model.
Okay.
And then I need to be able to do that in my code on the fly to do a fit. Because I don't have an equation. I have to solve a numerical model.
Yeah.
So
My tendency would be to say if you need to do that kind of on-the-fly type stuff, you probably do need to be writing your own code for it.
yeah, but this
I
is
mean,
nice because it has all the bounds on the parameters
Yeah,
and stuff.
yeah.
And the ones that I'm using don't.
I mean, I've never, I admit I'm not as good with scripting as I wish I was. So most of the time I just do this stuff, you know, I have a function I want to fit and I just do it by hand. As far as doing stuff at a bit more of a, how do you call it?
So basically,
Yeah.
as far as you know, you got to do all your curve fitting in the
I think so.
program.
I mean, I'm sure you
But
can
this
look
is
up.
open source, right?
Oh yeah,
So I can look up the functions.
absolutely, yeah. But I can't help you with that.
No. Okay, guys. 2 weeks we have another seminar. This will be Pablo. Yeah, he'll be talking about Linux tips and tricks. That's probably a good one. So I encourage you all to come. And maybe Eirik will organize a beer afterwards. Who knows? So plan on that. Save some money. And we'll go out and have a good time. All right. So I'll bring in the pieces and.